Our next, our next set of experiments is going to involve some additional objects. So the first one is going to be looking at how one of these rods interacts with paper. So now here, this is actually a charged rod and paper. So when we say a charged rod, we are now just using new terminology. This means a rod that has been, for instance, if it's a plastic rod rubbed with wool or a glass rod rubbed with silk. Now in this case, we're not specifying whether it's glass or plastic because either one will work. So after we have rubbed it, after it's charged, we see that it then will pick up little pieces of paper. So why is this interesting? We haven't done anything to the paper. This is just normal paper. We can again think about what must be happening with the forces when we bring in this charged rod. Initially, when there is no rod, we know that there's the force of gravity acting down, but then there's also a normal force acting up. If they're initially just sitting on the ground, then there is no acceleration. But once there is an acceleration upwards, we originally had our normal force down, our normal force up and our gravitational force down. But if we see these little bits of paper jump up, there must be another force. Obviously, once the paper's no longer in contact with the table, this normal force is gone, but this force is enough to actually overcome gravity and have the paper jump all the way up to the rod. So we know that there's an upwards acceleration, there's a net force up. So the important takeaway here is that this paper wasn't charged, that there is a force that appears to be an attractive force between little normal bits of paper and a charged rod. And we would call these bits of paper uncharged or neutral, and we see that this happens. This is something you can try out for yourself as well, even just using a comb and little bits of paper. Now, a second version of this experiment is to see that in fact we have an attractive force with any type of neutral object, where neutral means uncharged. So if I hang a charged plastic rod and I bring in a neutral plastic rod, there's again an attractive force. So remember, if both of these are neutral, nothing happens. There's no force. If, on the other hand, both are charged plastic rods, then there's a repulsive force. But if one is charged and one is neutral, again plastic, you have an attractive force. So this is interesting, and this is worth thinking about because depending on what you already know about charges, this might not actually make sense to you. So it's important to think through this and not just rely on your existing knowledge, because we're going to get into some physics here that's actually a little more complicated than what you might learn in a previous physics class regarding charge. But here we can see it very quickly with an experiment where we see that a charged object is attracted to a neutral object, and in this case both plastic rods. So the next thing we can do is actually look at how it interacts with the cloth itself. So the charged plastic rod is attracted to the wool that was used to rub it. Now, this might not seem that exciting because after all, we said that the charged rod is attracted to any sort of neutral object. But what we could actually do is a variation on this experiment where we have both the plastic rod that's been rubbed, and then we also rub the glass rod, but we put the silk here that was used to rub the glass. In that case, you get a repulsive force. So by using both our plastic and wool and our glass and our silk, we can actually look at different combinations of those four objects, and we see that the plastic and silk will have a repulsive force, the glass and the wool will have a repulsive force, while the plastic and glass have an attractive force. So another experiment here that's actually a little bit hard to do in reality is to actually try to find a charged object that will attract both plastic and glass rods that have been charged themselves. So we do know that this charged plastic rod and the charged glass rod will in fact attract each other. But what if we hung them far enough apart that we don't see them swinging together on their own? and we bring in an object that attracts both of them. Now what's a little tricky about this is that if this was a neutral object, it would in fact attract both of them. So we have to make sure that it's a charged object. How would we do that? Well, we would see if this charged object picks up little bits of paper. So if I have this object, say it's another type of rod, maybe a metal rod, maybe a rubber rod, maybe a wood rod, whatever you can think of, and we rubbed it with something, we saw that it did pick up little bits of paper, we could try putting it between these two rods and see if it attracted them. And in fact, there's nothing you can find that will do that. A neutral object won't pick up the paper and would attract these, but we already knew that. But any charged object, such that it picks up the bits of paper, will either repel the plastic or the glass. Now, this is fundamental. The argument we can later use this for is to say that there's no third type of charge. But really, the reason we say there's no third type of charge is because we've never found it, not because it can't physically exist. But if you try every object you can find, this will never happen. So this is a fundamental part of our model, and again, it's excluding a third type of charge. So we now get to the charge model itself, at least part one. We aren't getting into material properties yet. And what we're using really are frictional forces here. So think about that frictional forces such as rubbing is what's happening. There's also going to be systems where there's maybe rubber belts or metal brushes that also rub, but there's always some sort of frictional force that is changing a property of the object that we're going to call charge. Again, we're not saying anything about this yet. The word electron has not been written down yet. We're not using it. So the process of rubbing the object so that it now has a property called charge, we just call that charging. The more you rub it, the more charge you seem to have. Now, we seem to only have two types of charge. Right now we're going to call that plastic charge and glass charge. And we see that we can charge lots of other things, but it either attracts or repels plastic and glass as if it had the same type of charge. We've never found evidence of a third type of charge that attracts both plastic and glass. Whenever you have two like charges, so both plastic or both glass, they're going to repel each other. There's a repulsive force. They push away, but without contact. If it's opposite, so plastic and glass, they actually attract. They pull towards. Importantly, this is a long-range force. We're never talking about touching these objects. We will talk soon about what we might think about happening if things start touching, but right now that's not what we're talking about. These don't have to be in contact. We do see a larger force, meaning our hanging rod swings farther to the side if we decrease the distance. So the closer the things are, the larger the force. Now, something we haven't quite proven yet, but which later will be in our model when we talk about what's going on microscopically, is that a neutral object is an equal mixture of both plastic and glass charge. So neutral is not a third type of charge, it's just an equal mix of plastic and glass, and that the rubbing process separates them. And this separation is the reason that, for instance, wool and plastic are attractive, is that plastic has ended up with the plastic charge and the wool has actually ended up with the glass charge. The rubbing process separates them. So that's our charge model. We're going to talk a little bit about material properties before we actually start in the next section understanding what's going on in more detail.